From a distance, Earth appears to be a fully charted, familiar home. We look at this blue sphere and assume we have reached every corner. This confidence is built on centuries of terrestrial mapping. We have meticulously traced the coastlines and measured the mountains, leaving us with the impression that there is nothing left to find. However, the math tells a different story. More than 70% of our planet is covered by water. Here is the quantitative reality. Of that vast aquatic space, we have explored less than 10%. This leaves over 90% of the ocean completely unseen. It is a massive physical vacuum, unmapped and entirely removed from human observation. We are effectively strangers to the majority of our own planet. To understand the scale of this ignorance, consider the moon. Because of its visibility, we possess more detailed maps of the lunar surface than we do of our own deep ocean floor. Looking up through the vacuum of space is a matter of optics. Looking down through miles of dense, light-absorbing water is a matter of physics. Earth's greatest uncharted territory is not found in the stars. It is located directly beneath us, shielded by the ocean itself. At the surface, the ocean is defined by light. Sunlight penetrates the upper ripples, making the water transparent and familiar. But as you descend, the sun vanishes. In a matter of minutes, you move from a world of color into absolute permanent darkness. Here, the heat from the surface is gone. Temperatures drop until they settle just above the freezing point. Then there is the weight. Hydrostatic pressure, the literal mass of the water column, begins to press inward from every side with thousands of pounds of force. This environment is a physical wall. The combination of freezing cold and crushing pressure makes exploration down here more difficult than a mission to deep space. The 90% remains unmapped, because the very physics of the deep are designed to keep us out. Despite these lethal conditions, the abyss is not empty. Life thrives here in forms that look almost unreal. Without sunlight, these creatures have evolved alien features and bioluminescence to navigate a world that should, by all logic, be barren. These organisms prove that the biological standards of the surface world are completely irrelevant in the deep. While these creatures show us how life survives the pressure, biology is only one window into the abyss. This lack of visibility means that when physical events occur in the dark, we have no way to verify their cause. Because we cannot monitor 90% of the water column, we are left with data that current science cannot explain, ranging from unidentified acoustic signals to massive vessels that vanish without a trace. Even our limited sonar occasionally hits the outlines of massive geometric structures that do not match any known natural formations. These anomalies represent the absolute limit of our current technology. They are the artifacts of a world we can detect but cannot reach. It is important to remember that these phenomena are not science fiction. This alien landscape is tied directly to our own. It is the foundation of the planet we live on, and the deeper we look into our own world—
This is the bathypelagic zone. It begins where the last remnants of sunlight vanish, leaving only a vast, cold void. Biology on the surface is fueled by the sun, but thousands of meters down, life has found a way to persist without a single photon of solar energy. The creatures here share little in common with the life we know. Their anatomy and behavior are dictated by an environment that is hostile to almost every known form of terrestrial biology. Survival in this darkness requires a complete departure from surface-level logic. To exist here, an organism must follow a specialized biological protocol designed for the deep. Where the sun cannot reach, organisms must generate their own illumination to navigate and hunt. This is bioluminescence. It is a chemical reaction within the body that creates light with almost zero heat waste. For many, this light is a predatory tool. Anglerfish and jellies dangle glowing lures into the black, drawing in smaller creatures who mistake the pulse for food. Others use light as a defensive shield. Sudden, intense flashes can temporarily blind a predator, or specialized glowing cells on a belly can mimic the faint light from above, making the creature invisible to anything looking up from below. In the emptiness of the open water, distinct rhythmic pulses allow individuals to find mates or mark territory, acting as a visual language across the darkness. Light here is not a luxury. It is a weapon and a primary means of communication, making survival possible in a world of absolute night. Beyond light, survival is a matter of physical form. Many deep-sea inhabitants have evolved entirely transparent bodies. Without shadows or terrain to provide cover, transparency is the most effective way to blend into the surrounding water. But the need for food drags more aggressive adaptations, like the development of massive, distensible jaws and needle-like teeth. This diagram shows the specialized skeletal structure that allows these predators to swallow meals much larger than themselves. In a habitat where food is extremely scarce, a hunter cannot afford to encounter prey it isn't equipped to eat. Because a predator may go weeks or even months between encounters, its biology is optimized to capitalize on every single opportunity, no matter the size of the catch. Success in this environment favors the extremes, either the ability to remain completely unseen or the physical capacity to consume massive amounts of energy at once. There's a third factor that defines life here, an invisible force that exerts itself from every direction. This chart compares the pressure at the surface to the weight at the bottom of the trench. In the abyss, the water exerts several tons of force on every square inch, a pressure that would instantly collapse the lungs and crush the bones of a human. Deep-sea organisms avoid this by lacking gas-filled spaces like lungs or swim bladders. Their tissues are composed of water and specialized proteins that maintain their shape and function even under these immense loads. This specialization is so complete that many of these creatures cannot survive at the surface. The lack of predator causes their delicate cellular structures to lose their integrity and fail. They are physically bound to the deep. The same environment that would destroy us is the only place they can maintain their biological form. To understand these creatures is to realize how vast and inaccessible their world truly is. This model represents the total volume of our deep oceans. The highlighted section shows that despite decades of research, we have hardly touched the vast majority of this space. Almost every time a submersible reaches a new depth or unexplored ridge, it returns with footage of a species that has never been seen by human eyes. If every targeted exploration reveals a new organism, then the ratio of explored volume to new discoveries suggests that millions of species likely remain hidden in the dark. The deep ocean follows a logic we are only beginning to map. And as we look into the black, we must accept that its most significant mysteries are still swimming just beyond our reach. When you descend past 1,000 meters, the light from the surface fades completely. Down here, human eyes are entirely useless. To navigate this darkness, we depend entirely on external sensors. We bolt high-definition cameras and acoustic arrays to specialized submersibles, essentially building artificial eyes and ears to map the abyss. This global ocean topography map shows exactly what we expect to find. We see clearly defined underwater mountain ranges, tectonic ridges, and predictable biological activity. The math checks out. But as we push our probes deeper, we start to encounter readings that our current databases can't identify. High-fidelity sensors are capturing signatures that seem to break away from the expected patterns of deep-sea geology and biology. It leads to a difficult question. How do we process empirical data when it starts to diverge from our established models of the deep? One of the clearest examples of this divergence occurred in 1997, when monitoring stations recorded a massive, low-frequency sound, now known as the bloop. Looking at this map, hydrophones picked up a powerful acoustic signal rippling across the Pacific from thousands of miles away. The audio profile matches a living creature. But in this split-screen data comparison, the 1997 waveform completely dwarfs the volume limit of a blue whale. Because generating that much decibel output defies biological limits, marine acoustic experts continue to debate the true source of the recording to this day. Our underwater microphones are picking up the signatures of kinetic events so large, our current biological models simply cannot account for them. The anomalies aren't limited to passive listening. Surface fleets continuously run active sonar sweeps to track movement beneath the waves. During these routine sweeps, military and research vessels occasionally ping unidentified objects moving deep within the water column. This sonar interface illustrates the mechanical problem. Tracking displays measure targets traveling at velocities far exceeding the thrust of any modern nuclear submarine. The physical impossibility becomes clear when the tracked target executes a sharp right-angle turn. It changes vector instantly without losing speed. After displaying these maneuvers, the targets frequently vanish from the tracking displays entirely, leaving behind no physical trace or acoustic wake. These kinetic tracking events leave us with hard proof of a severe gap between what our instruments clearly detect and what physics actually allows. The friction between our data and reality extends all the way down to the solid crust of the ocean floor. This high-resolution topographical map of the deep-sea bed is exactly how we chart the geography of the abyss. But occasionally, this specific type of mapping reveals localized structures that appear entirely unnatural. Hidden deep within the silt, geologists are finding perfect shapes and highly precise geometric patterns sitting completely undisturbed. Natural geology is driven by chaos, asymmetry, and random erosion. Finding perfectly smooth, right angles resting on an uneven seabed defies the normal geological process. While oceanographers can eventually trace some of these shapes back to rare natural phenomena, others stubbornly resist any easy classification. The seabed itself contains permanent physical evidence that continues to challenge our basic understanding of how the Earth forms under pressure. We possess the raw materials of discovery. We have the audio waveforms, the high-speed sonar tracks, and the geometric seafloor maps. We have flawless data, but we lack any real context.
The combination of these massive acoustic signals and kinetic tracks describes a highly active environment, one that produces phenomena we currently have no way to quantify. Despite our satellites and submersibles, we have yet to map more than a fraction of the deep-sea floor. The ocean remains largely unmonitored, holding on to its data more tightly than our technology can currently extract it. The sheer atmospheric pressure and immense vastness of the water column virtually guarantee that some of these anomalies will never be resolved. We spend billions looking at the stars, but our own planet holds physical mysteries just as alien as deep space.
The Earth's oceans cover over 70% of our planet. They form a massive physical barrier that has, for most of history, remained impassable. We have reached an era of total surface mastery, using satellites to map the continents. Yet the deep ocean remains a massive, unmapped blind spot. This gap in our maps doesn't exist for lack of curiosity. We haven't ignored the deep. We have been kept out by its physics. The first barrier is hydrostatic pressure. The water's weight compounds until it can crush titanium. Light vanishes similarly, leaving the bottom 90% in absolute darkness. Finally, the terrain is a jagged landscape of trenches and cliffs, making navigation impossible. Our maps are empty because the planet's architecture aggressively resists human entry. Because of these conditions, oceanography is a slow and expensive process. A single mission can take years to fund and weeks to execute, only to observe a tiny sliver of the seafloor. To understand the scale of our limitation, imagine trying to map the entire North American continent using nothing but a single narrow flashlight beam. But the small patches we have illuminated show us that the abyss is not a void. Almost every time we send a camera to the bottom, we find biological species that have never been documented by science. We discover geological structures and chemical vents that challenge our previous assumptions about how the Earth's crust functions. These discoveries immediately raise new questions about how life can sustain itself without sunlight or oxygen. We are caught in a feedback loop. Every single new data point branches into several unknown variables. The more we learn, the more we realize we don't know. This pattern of discovery points to a biological density we are only beginning to measure. The significance of these missions isn't just the data they collect, but the evidence they provide that the vast, dark ocean is intensely alive. This cube represents the ocean's total volume.
The gold sliver is the tiny fraction we've seen. The remaining 95